Most senior machine learning engineers begin their day in a Jupyter notebook. It is a comfortable space where experimentation flows without interruption. You write code, execute it, and see the results immediately. The environment is forgiving. You can import a library, tweak a parameter, and run a cell without worrying about the underlying infrastructure. But then comes the moment you have to move that model out of the notebook and into a scalable Kubernetes cluster. This is where the friction begins. It is not just a technical hurdle, it is a fundamental shift in how you think about software delivery. To understand the landscape, we need to look at three distinct approaches engineers take to bridge this gap. Each one represents a different philosophy about control, convenience, and complexity. The first approach is the native Kubernetes method. Here, the engineer treats the machine learning model exactly like any other microservice. You package the code into a Docker container. You write a Helm chart to define the deployment. You configure the GPU resources and the networking policies manually. This path offers maximum control. You know exactly where every byte of data goes, but the friction is immense. You are responsible for managing the cluster health, handling scaling events, and ensuring that the Python environment inside the container matches the one you used for development. A single mismatch in a library version can cause the entire pipeline to fail. Consider the second approach, the managed cloud platform route. In this scenario, you hand the model over to a service like Amazon SageMaker or Google Vertex AI. You upload your artifact, configure the instance type, and the platform handles the rest. The friction here shifts from infrastructure management to cost management and vendor lock-in. You gain speed. You do not need to worry about the Kubernetes API or the underlying nodes. However, you lose the ability to customize the runtime environment deeply. If you need a specific version of a CUDA library that the managed service does not support, you are stuck waiting for the provider to update their images. This creates a bottleneck when you are trying to deploy cutting-edge research models that have not yet been standardized by the cloud providers. The third approach is the emerging paradigm of agentic operations. This is where the research from late 2025 and early 2026 becomes critical. We are moving beyond static models that simply take an input and return an output. We are building systems where the model acts as an agent. It plans its own steps, it calls tools, it reasons through complex problems. Deploying an agent to Kubernetes is fundamentally different from deploying a static prediction service. An agent requires state. It needs to remember previous interactions. It needs to manage external tool calls securely. This introduces a new layer of friction regarding state management and latency. If the agent gets stuck in a loop or hits a rate limit on an external API, the entire cluster can become unresponsive. Let us focus on the core friction points that senior engineers face across all three of these paths. The first major pain point is environment drift. In a notebook, you might be running on a local machine with a specific version of Python and PyTorch. In Kubernetes, you might be running on a managed node with a different kernel version. Even if the code looks the same, the binary behavior can change. This leads to the classic problem of it working on my machine but failing in production. Engineers spend hours debugging why a tensor shape is different or why a specific optimization flag behaves inconsistently across environments. The second friction point is resource contention. Kubernetes is designed to schedule workloads efficiently, but machine learning workloads are greedy. They want all the GPU memory they can get. When you try to run multiple models on the same cluster, they fight for resources. One model might spike in memory usage and cause another to crash. This requires sophisticated scheduling policies that most standard Kubernetes configurations do not have out of the box. You often need to implement custom operators or use specialized scheduling frameworks to prevent these collisions. The third friction point is observability. In a notebook, you print the output to the screen. In production, you need to log metrics, trace requests, and monitor latency. When you move to a distributed cluster, a single request might touch 5 different microservices. If the response is slow, figuring out which service is the bottleneck requires a level of tracing that is often overkill for a simple model. Yet without it, you are flying blind. You do not know if the model is degrading or if the infrastructure is struggling until the users complain. This tension is becoming more acute as the field evolves toward agentic systems. The research from 2025 and 2026 highlights a consensus that we are moving toward autonomous agents that require complex tool planning. This means the deployment strategy cannot be a simple container restart. It requires a system that can handle retries, timeouts, and state recovery without losing the context of the agent's conversation. This adds significant complexity to the toolchain. You are no longer just deploying a function. You are deploying a behavior that must be reliable over long periods. Furthermore, the drive for performance often clashes with the need for safety and interpretability. As models become more capable, understanding why they make a specific decision becomes harder. In a production environment, a model making a mistake can have real-world consequences. You need to balance the speed of deployment with the rigor of testing. This is where the friction points become most painful. You have to decide how much you trust the model versus how much you rely on human-in-the-loop checks. There is no single perfect solution for every situation. The native Kubernetes path is best for teams that need deep customization and have the engineering resources to maintain it. The managed platform path is ideal for teams that want to move fast and do not want to manage infrastructure. The agentic approach is necessary for complex systems that require state and reasoning capabilities. But regardless of the path you choose, the friction remains. It is the friction of moving from a flexible, experimental environment to a rigid, reliable one. The industry is maturing. We are seeing a shift from theoretical foundations to practical integration. The tools are getting better at handling the environment drift. New frameworks are emerging to manage the state of agents. But the fundamental challenge remains. It is a challenge of governance and alignment. As the speed of development outpaces the creation of regulatory frameworks, engineers must build their own safety nets. You must ensure that the systems you deploy are not just fast, but also safe and explainable. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.